Just double checking that we're ready. All right, let's do this. So, welcome back to the MathSoc presenting MATH2521 2621 Complex Analysis Revision Seminar. This is part 2. We'll be continuing off from where we left off last time, just doing a little bit of integration before we do the rest, which will just be series and transforms. Alright, so everyone just double check. Feel free to ask questions during the event. And yeah, let's get into it. So, we got Cauchy's integral formula. Okay, so this is just fundamentally saying that if you have some manner of simple pole inside a domain, so let's say we have a pole in there and we're doing a closed integral that encapsulates it, then we have a very, very cool formula just to give you the answer straight away. So that's pretty much all that is. So now we'll just dive straight into the question, so we're getting some experience using it. Right here we have a integral about the circle with radius 3, centered about the origin, and we can see 2 poles on the denominator. Okay, and just working off of this, we should be able to see that both of these are simple poles. The domain is holomorphic, excluding this point, and we should be good moving from there. So, understanding this, we can break it into partial fractions. So now we're just dealing with 2 simple poles. We can break it up into 2 integrals even, and then just apply Cauchy's integral formula, where the result is just given by 2 pi I times the function at that point. Okay, so we get 2 pi I times the function at 2 and 2 pi I times the function at minus 2, giving us the desired result. Okay, fantastic. Let's keep it moving. So Cauchy's generalized integral formula is provided here, and it's fundamentally just saying that now the actual value of we'll learn to call this residue, but the value is dependent on the degree of this pole. Okay, and so from there we just take more derivatives and we divide by a higher factorial. Let's jump into another example, and if anyone has a question, just feel free to wave your hand or just put it in the chat. Let's do this. So here we have a basic example. We're integrating about the circle of radius 4 of z squared on z minus pi all cubed. Now, this one looks like f. This one looks like our pole of degree 3. And so we'll just scroll back up a little to our formula, and we'll just use that as required because we understand that pi is within our boundary. Okay, so we should get 2 pi I divided by, mind you, an important distinction is just understanding the function is holomorphic, excluding that point. Okay, so 2 pi I on n is 2 in this instance, so we take 2 factorial times the function z squared differentiated twice will be 2 at the point w, which is pi. So, as required, the desired result. Alright, now we're going to have a bit of a more difficult question. So, we are going to try and show that if f is an entire function such that the absolute value of f is less than z, the absolute value of z to the power of k for a positive integer k, that then f is a polynomial of degree at most k. Alright? So the trick with this thing is understanding what this means. And what this means is for a polynomial function that if, let's say, degree of f is equal to k, if we say this, then that means that the behavior of f of z at a sufficiently large z, so let's say z is much greater than 1, then the magnitude of f of z is comparable to the magnitude of z to the k. Okay? This is just a little thing we can work by with intuition, but we want to be a bit more rigorous than that. So what we should go ahead and say is that given this intuition, we understand that the behavior of our polynomial is widely determined by the highest power when we hit sufficiently large z. So for the derivatives of derivative of f k plus n many times for some integer, positive integer n, we should get 0. Okay? Because that's just saying, okay, the maximum power over here has been kicked off. Okay? So let's go ahead with that. We understand that the derivative can actually be determined using Cauchy's generalized integral formula. And so what we'll do is identify a contour and then evaluate the integral. Okay? So let's do this. We understand from our circle inequality back yesterday in part 1 that we can change this difference to a change in difference in magnitudes. Okay? And then likewise, we can still apply k plus n plus 1 as the exponent, but all we really care about is this big R value, okay? Because if we choose a sufficiently large R, it shouldn't matter what our magnitude of W is, okay? So we do that, and we recognize that the denominator, the exponent attached to R, is bigger than the numerator. Therefore, as R goes to infinity, we have this magnitude goes to 0, okay? So that is quite literally the ML lemma, max on length. I forgot the proper name, but just the maximizer. Given our integral is just a circle with radius big R, we multiply by that. And for all n that is 1 or greater, recognize that it has to be at least 1, we observe the result. And therefore, since the magnitude goes to 0, the actual value goes to 0, which is what we set out to prove. Fantastic. We can tack on a little extra bit about the fact that f is an entire function, so it's differentiable everywhere. So that's pretty much just saying that we're allowed to pick a sufficiently large R, okay? Because if it's not entire, then there might be some bound at which it is no longer differentiable and we're no longer allowed to use this integral, okay? Let's move on. All right, so we got Louisville's and Moira's theorems. Basically, Louisville says that if it is bounded and entire, then it is constant. I'm pretty sure where it comes from with this is that if you have a 0 somewhere, then there must be some last 0 of some sort, at which point it will continue to grow unboundedly. And so, if you are bounded, you got zeros everywhere, kind of have to be constant. Anyways, Moreira dictates that it's like the converse of our Cauchy-Gaussat theorem, I believe. Whereas we're just mentioning that if we have a closed integral for, a closed contour, and we integrate about it, then f has to be holomorphic if that integral equals 0, okay? It's an interesting result. We don't usually get converses working. Anyways, here's an example. Let's try and use Louisville. Louisville goes ahead and says that, okay, I'm entire, fantastic. Am I bounded? How do I get bounded? Well, I have to try and get a constant somewhere. I can't see a constant immediately, I have to divide, right? So let's define a function g that is the division of f by cos. Therefore, the magnitude of g is less than or equal to 1. Sounds bounded to me. And so, since we have the composition of complex differentiable functions, it must also be entire, right? And therefore, just by defining all the points as limit points, just to ensure that we're not stepping on anyone's toes in the division by cos z, we just ensure that our limits are defined and work, okay? Fantastic. So this is just a little statement ensuring that we don't have any discontinuities right now. Moving forwards, we've determined it's bounded, we've determined it is entire, and therefore it is a constant, right? We love it. But there's something we need to take care of, okay? First of all, magnitude has to be less than or equal to 1, it just can't be any constant, but also that bringing it back to the point, we're dealing with f is a constant times cos of z, okay? Fantastic. That'll be the end of integration as we know it, and we'll be moving on to series, okay? So, any questions so far? All good? All right, let's do it. So, power series. First things first, let's just hit off with a definition. It is a sum of coefficients attached to increasing index of my center, okay? And this gives us a radius of convergence. There are a couple ways of defining what the actual radius of convergence is. A typical one used is just the ratio test, which is usually fantastic, but also, I mean, if we want to be a little bit narky, we can define it by as it was, which is the supremum of an, so that's just your nth coefficient, taken to the nth root, and then the reciprocal of this. Okay, and this is the supremum on n equals 0 up to infinity. All right, so that's just the hard definition of it, which we can usually derive using just the limit. Okay, it's a funny thing just because it tells us at what point are we really going to 0 or going to infinity. Yeah, anyways. So that's power series, that's that. Something to note is that integration and differentiation is a powerful tool that we can still use in power series, okay? Especially when we have n terms including n, that are not in the exponent. All right, so let us go through a question. It's a little dated, but it still works. Let's think about this. So radius of convergence, looking right here, -3, fantastic. Let's determine, sorry, not radius of convergence, that's meant to be center, my bad. And then radius of convergence, let's run it through the limit test, okay? So that'll just be an on an plus 1 equals n on n plus 1, goes to 1, radius is 1. Fantastic. If we wanted to be going straight from definitions, we recognize that an to the 1 on n, it approaches 1, and reciprocal of 1 is still 1. Okay, and this is sometimes it's a bit hard to show, which is why we just enjoy ratios. Anyways, moving forwards, we recognize that we need to find an expression for h as an elementary function. Okay, so elementary function We don't want any of this sigma stuff. So let us break it out. Mind you, I gave you a little hint before. Oh, oops. Let's not make too much of a mess. Yep, there we go. Gave you a little hint before, just about the fact that we're looking at an n. Differentiation and integration are going to be very helpful. So that is exactly what we're going to do. To get rid of an n here, we have to integrate this form, okay? But understanding we're dealing with the same thing, we integrate and differentiate just so that we can look at it differently, okay? And then we can run it through different processes. So over here, we're getting rid of the n so that we can express this sigma, this sum, as a geometric sum, okay? And this is really important, mind you. This is, they might have mentioned, it says for all z for which the sum converges. So we are just really talking about, okay, since it converges, the geometric sum should be finite, therefore the magnitude of whatever denominator I get should be within bounds. Alright, where was I? I was here. Alright, so we went ahead and we integrated it by first of all taking a power out so that our exponent was appropriate, integrate and differentiate at the same time so that we get z plus 3 to the n inside, geometric sum, and then go back to differentiate it. Okay? Fantastic. Another one. Another sneaky n. Now, let's run through this. We want to find the center and radius of convergence and the expression for f as an elementary function. Okay? I think I forgot one little bit on this question. Where is it analytic? This is pretty much just saying, okay, define the ball. You go ahead and you do it, and you say, okay, centered about -3. We told you the radius is 1. Bam. Anyways, back to the point. We're going to do this. Center, we can go ahead define the center as just, okay, when is this thing 0? We get 5 on 2. Fantastic. And then we want to find the radius ratio test. We see a sneaky 2 here, so we've got to be a little careful there. We can normalize the form into the summation from n equals 1 to infinity of 1 over n plus 1 times 2 to the n outside of z minus 5 on 2 to the n. Alright, so just understanding this, our ratio is dominated by 2 to the n. So, ratio test, we'll just do it again. We get 2 to the n on n plus 1 times by n plus 2 on 2 to the n plus 1. Fantastic. Which just goes to 1 and 2. Okay, we got our radius, we're happy. Fantastic. Next up, we want the expression for f as an elementary function. Now, before we mentioned integration differentiation, it's not in the right mode just yet. Okay, so we're going to make it. We're going to make it into the right mode. And the best way to do this, I would say, would be to go ahead and shift another one of these inside there. So we can multiply by and divide by z minus 5 on 2. And then we can differentiate our form to get this n plus 1 out of the equation. Okay? So we'll do that as they have done here. They multiply by z minus 5 on 2, and then they differentiate it to achieve this. And then they'll just work backwards to determine what f of z is. Now, mind you, as a geometric series, this does converge because we've defined it within that bubble of, 5 on 2 as the center of the ball and then a half as the radius. And now we will move forwards to recognize this is our ratio. So we just need to go 1 over 1 minus this value, okay? And then we will multiply, which gets a little, no, it works. They've kind of did it back to front, I feel. Actually, no, never mind. You end up getting the ratio, which is 1 minus the 2z minus 5, which brings out to here and here, but then you multiply by your other term, and it works out. All right. Now, we have just determined the differentiated value, okay? And we've put it as an elementary function. All that's left is to integrate, then divide, right? So we integrate, we have a little bit of fun, but now we have a constant of integration. The only point we can really sub in here is the center of the bubble, okay? The center of our circle, which is just going to be 5 and 2, okay? Plug in 5 and 2, both sides go to 0, fantastic. 5 and 2 over here. This one is going to be just log of 1, so C ends up being 5 and 2. Fantastic. And last of all, just divide. You guys got this. All right. Taylor series, it's just like how we formally determine our power series associated to certain functions, but not too much to stress over. We've done first year. Maclaurin series also exists. All right. Yeah. Stuff we're expected to know is just very, very simple stuff like e to the x and potentially sine x. You can derive sine x from e to the x if you really feel like it. But as long as you got that in your depth of imagination, you guys got this. It should just be summation from 0 to infinity of, man, I hope I don't get this wrong, x to the n on n factorial. Bam. But yeah, that is just e to the x. And now we're just going to manipulate this, do a little bit of algebra. We're going to multiply it by z plus 2, and just still taking Taylor series about a point, okay? Maclaurin series. So, yippee, we were correct. We replaced z with 3z, and then we really just want to group this into there, which we distribute, fantastic, but we want to rank it according to our powers of z, typically, okay? So we can see on the left term, we got k plus 1, so we just have to adjust where we're measuring from, and then we'll be happy, okay? And from there, we group it, and we are dandy. All right. Any questions so far? Enjoying it? All right, nice. Now we have Lorentz series. Lorentz series is basically a power series, but also goes into negative indices. So it also accounts for divergence, I believe. I think that's one of the things. Anyways, this is a very important fact, and it lets us analyze functions a little bit deeper. But really, all we want to care about is the fact that Lorentz theorem tells us that the coefficient Cn is given by 1 on 2 pi I integral around the boundary of a function over z minus z0 n plus to the power of n plus 1. z0 is where we are measuring about, so that's just, this is whatever thing in the middle, okay? Yeah. All the stuff, typically this makes annuli that we need to just calculate about. But I guess the real trick in this is that we want to be careful. If we have, okay, the big trick that we're going to be using for this is just geometric series, okay? So we recognize that if I have r plus r squared plus yada yada plus r to the n, this ends up being equivalent to 1 minus r to the n plus 1 on 1 minus r. Fantastic. However, the big trick in this is when n goes to infinity, we want r to the big N to go to 0. So that implies that the magnitude of r is less than 1, which would make it equal just 1 over 1 minus r. So the trick that we're going to pinpoint right here is that this convergent sum that we're defining, it needs to have r such that it is less than 1. And there's a trick we can do for this. We can go ahead and multiply, okay? We don't want r here, so we'll just divide by r there. Multiply and divide. So we go 1 on r outside of 1 over 1 on r minus 1, okay? Because those are equivalent. And now if r was greater in magnitude than 1 on r isn't, and we still have a convergent sum for it. And it just works, because this value, when I take it to the nth power, will just reduce back down to 0. Yeah. All right. So that's the trick. I'll just quickly mention if magnitudes are greater than 1. Yeah. All right. So let us go ahead and run through this example. First things first, we want to find the Lorentz series given z plus 1. Okay, given z plus 1 is greater than 1. This is the basis we are surrounding our Lorentz series in. This is our center, 1. Okay? And so if you wanted to draw it, we got our Argand diagram. Can never get enough of these. Here's 1. Here's the open circle about 1. And we're just dealing with the outside. Alright. So, quite frankly, we just want to decompose this first. Partial fractions, our best friend. And then we want to ensure that we are expressing it in terms of z minus 1 of all things. Okay? Now, there's a couple of things we want to highlight just in this step. Okay? Since we want it to be about 1, we have this one is a distance 1 away. This one is a distance 1 away. Okay? Now, given that the distance of z from this point is greater than 1, then we have a little issue. We go ahead and we write 1 on 2, 1 on, we write z minus 1 plus 1, minus 1 on z minus 1 plus 1 on 2 multiplied by 1 on z minus 1 minus 1. Okay? The issue here is wondering the magnitude of this. And it's told us the magnitude is greater than 1. So, we scroll up a little bit. We have to apply the reciprocal. Okay? And so, we observe just over here. We do exactly that. Okay? We multiply and divide. Multiply and divide. Alright? So, moving forwards from here, we format these back into the sums that they were, just pulling backwards from what we were doing before, and reconstruct it in the desired form. Okay? Now, the tricky bit here is the fact that, n from 0 and beyond. Fantastic! There's no negative indices. There's none. Because these two cancel with this one in the initial case, and then work together on every... Sorry, other way around, my bad. Index is on the bottom, so those are our negative k cases, my bad. And so, we write, they cancel in all of the cases being even, being positive, and being minus 1. Okay? And so we're just left with their summation on the rest of the negative odd numbers. Alright? Never mind. Okay. Another question. We're just gonna, I think we can just glide through this stuff right now. So we'll just take it easy. No need to rush too hard. We got the full hour and a half to go. So Math 2621 2015 final question 2I. We're given a already dissolved partial fractions. Fantastic. Find the Lorentz series for f in powers of z minus 2 that converges when z equals I. Okay, this is the funny bit. All right, powers of z minus 2. So we already know we're going to be expressing it as 2 over z minus 2 outside of plus 2i minus 5 on z minus 2 minus 2. Great. Now, typically, we normalize these. So we'd have to divide and multiply by 2 plus 2i on this one and minus 2 on this one. Okay? But that aside, we recognize that for this to converge, the magnitude of z minus 2 would have to be less than 2 plus 2i. Okay? Otherwise, we'd have to take reciprocal. And so this gives us the boundary of root 8. This one gives us the boundary of just 2. And we're saying that, okay, z equals I. Well, when z is equal to I, the magnitude of z minus 2 is going to be root 5. Okay? So since it is root 5, it is squat in the middle, and we get this kind of thing going on. Yes, it is less than this. Fantastic. That one is great. This one, not so much. We have to take the reciprocal of that. And so, we did. We did. All right. Moving forwards, we pretty much just go about our business, reformat it back into two sums as required, and then just analyze our k values and where our z's are. Okay, so we can clearly see on the right we're going to be seeing k values, index values being -1 and lower, because we start at, first of all, k being 0, being also divided by z minus 2. Okay, so we're starting at -1 and we're moving down. For the first one, we're starting at 0 and we're just moving up. Okay, just moving up for that one. Fantastic. So we can just go ahead and outright split our coefficients up. Mind you, coefficient is attached to here, here, and over here. So this will just be for the greater than or equal to 0 for k cases. And then for k cases less than 0, we get the -5 and the 2 to the k. Yeah, ignore this. Should be -5 times 2 to the k. I believe. Yes. Actually, the k plus 1 factors out. So this will be looking at case k plus 1. So when we push that back to case k, this comes a -1. Alright. So that's just for this one. That's what it should be. Anyways, moving forwards. So now we got singularities, right? Singularity is basically a discontinuity or just undefined points. Okay, that's the easiest way to think about it, but then we can apply a more rigorous definition to them. Okay, so it is a point that is holomorphic on the punctured so that is to say that at a certain point it is not differentiable there, but surrounding it within some radius is differentiable. So it's just a pole. Moving forwards, we define them in one of three ways. Okay, so and it's all dependent on their Laurent coefficients. Okay, so ideally, we've gone ahead and defined their Laurent coefficients. This is for C0. This one's for C minus infinity. This one is for C infinity. Okay, and points in between. Fantastic. If there are no integers n less than 0 with Cn not equaling 0, let's get rid of the double negative and just say that, okay, if all of these are 0, then it is removable. Okay? So that's to say that, okay, whatever pole you were thinking about, it cancelled out. And so the limit there still exists. It's like having a function that just has a circle in it. Okay? It doesn't jump to extremes. It's very well behaved. So that's the first one. Second one, we say that there is a finite number. So this is just going to be C minus 5. Just going to use 5 for that case. If we do this, and these ones are not 0, so they're actually real valued, and then the rest are 0, going backwards from there, then what we have is a pole, and a pole of order 5, okay? Just because there's 5 degrees of pole in that direction. Moving forwards, if we instead say there's infinitely many that are not 0, okay? So we can keep on finding pole values going to the left, coefficients that are non-zero. Then what we have is an essential singularity. We won't really be dealing with them in this course, but it's just something funny to deal with. Alright, next up, some theorems, okay? So it's just another way we can manage identifying these without actually having to determine their Laurent coefficients, because that is a hassle. If the limit as z approaches your point that you're analyzing of your function exists, it is a removable singularity, okay? So that is to say that I have a function and its limit, bam, I just define it there, and it works, it's fine. Otherwise, there is a pole, okay? And typically poles, let's consider it in a real manner rather than complex, just for the sake of visuals. If there is a pole there, and it is finite, okay? It's finite degree, so z to k, and we can find a limit for multiplying it, so that is we move forward into a new graph by multiplying by z minus z0. Then it is a pole of a certain order, okay? And we'll just add a k for some value. Furthermore, if we have an essential, then there is just no way for us to actually determine a limit, okay? Fantastic. Let's keep on going. So, furthermore, I mean, I kind of already mentioned this. We got poles of orders, and simple just means 1. Order m just means, ideally, you have z minus z0 to the power of m as one of your factors. And that's all that it is referring to in terms of z0, okay? So you'd kind of subtract zeros from poles in this instance, but yeah, fantastic. We'll be dealing with that in these examples. All right, let's do this. So 2016, question 2.4a. Classify the singularities, okay? So remember, there's removable, there is just a pole of a certain order, and then there is essential, okay? And we already told you we're not going to be dealing with essential, so 50-50. Two poles given by the denominator must be plus and minus I pi, just because we're squaring to a positive number. And now we just consider the limits. On the numerator, is it finite? Is it defined is it non-zero when we go to these ipi minus ipi values? Yes, it is defined. It is non-zero. Therefore, it is not removable. Okay? For it to be removable, it would have to be at the very least of the form 0 and 0. Okay? In which case, we would apply L'Hopital's rule. But we observe that is not the case, so we multiply out the z minus the root. Okay? Which yields us our functional value there. Okay? Fantastic. Since we were able to define the limit, it is a simple pole. Lovely. Moving forwards, similarly, we look at the other root, so this is now for the minus ipi, and we see the same thing. Now we're going to start talking about residues. So, what is a residue? A residue is just the first negative coefficient of a function at that point. Okay? Now, residues only exist for singularity points. I guess that's one thing we didn't mention here. But actually, I suppose a residue can exist for a non-singularity point, but we only really use residues at singularity points. Okay? Fantastic. And so, we can calculate residues using this formula. And it can be derived just from this, but we just want to be careful in how we use it. But nevertheless, let's get cracking. So, here is an example. We have a sinusoid on the denominator, so that is no longer just a standard polynomial. It has zeros here, there, and everywhere. So, what we're going to do is consider the singularities at just z equals k pi. K is integer. So, we recognize that we need to count degrees. Now, when we count degrees of sine and its zeros, we can actually say that sine of z, let's just consider z on sine of z, okay, as z goes to 0, okay? We recognize, we formally acknowledge, this is as z goes to 0, this goes to 1, okay? Therefore, it is always going to be a removable discontinuity, and we only have simple poles given by this reciprocal of sine, okay? This is a really important point, which actually makes this entire thing possible. It's this comparison to more basic limits. Okay, we apply L'Hopital's, sure, but it's recognizing this for this question. So we say sine on its own has a degree of 1 as a 0 whenever it is 0. So let's look at z equals pi. At z equals pi, sine pi is 0, a simple 0. So we square it, we get a pole of degree 2. But on the numerator, we also have a 0 of degree 2. It cancels out. It has to be removable. So the residue equals 0. Okay? It is removable. Because, I'll just point this out, the residue is given by derivative times that. Now, n in this case is 0. So we just take the function at that point, which will be going to 0. Okay? Residue is 0. Next up, we have z is 0. So now we have 1 0 on the numerator because of this guy. And then we have 2 poles being the zeros of the denominator. Therefore, simple pole. Fantastic. We can do this a little bit more formally by just saying, oh, okay, the limit does not exist, but then when I multiply by z, the limit now exists. But, I mean, quicker ways are better. So we multiply by the z. We determined it was a simple pole, so now we just follow through with the formula. And so determine the limit, we recognize that this is just going to be 1, so we just 1. Sub in z is 0, pi squared. Okay? Nice. Let's keep on moving. Just double check. Any questions? All good? Not all good. Oh, good. Let's keep it going. So now we've exhausted all the possibilities of zeros on the numerator. We only need to consider the poles given by the sinusoid. So all of them will have a degree of 2, and there's nothing that's going to change, and so we just simply define it as such. But there's a little issue here. We do not know the residue value at this point. Okay? We do not know how to deal with the what we don't know how to deal with is, just a moment, the limit of z to z0, well, z to k pi, of the first derivative, d on dz, of z minus, it's just, z minus k pi to the power of 2 times z minus pi squared all over sine squared of z. Okay, we don't know this value. This gets really messy because we got sine of z as well as more powers to deal with. If we wanted to deal with this how we know right now, we would go ahead and hurt ourselves doing product rule. But we don't want to do that. Instead, we recognize it is just the coefficient of c minus 1. Okay, of z to the minus 1, which is c minus 1. So we go ahead and determine the Lorentz series. I mean, we can use Taylor series for this, but it's just grabbing it from the Lorentz series. First of all, we convert sine into this format just by chucking it into its Taylor series centered about k pi, which we just recognize from the, there are a few ways we could do this. You could recognize it from the coefficients of the derivatives of sine, or you could just understand that sine squared's behavior about k pi is very similar to its behavior about 0. Okay? So there's that. And so we obtain this. We need to process the reciprocal. Now that we're processing the reciprocal, we want to factor out a certain value. Therefore, we can start talking about a summation. Okay? So they make this little bit of a goofy situation by going ahead and determining this little highlighted bit as a ratio that should be less than 1 in magnitude, which I find rather amusing. But they move forwards with that, and good on them. They managed to move it into the numerator, and it is actually a sum now. We can deal with coefficients. Lovely stuff. Now, that is the 1 over sine squared dealt with as an elementary, not as elementary, as the form of Lorentz series. Now we just need to multiply it by our remaining poles. Remaining equation. And so, what this would give us would be, mind you, we do have to recenter it about z minus k pi. And so, we just look at the coefficient of z to the minus 1. Z to the minus 1 is dealt with by the fact that this is starting from I is 0. For every I greater than 0, this bit up here is very unhelpful because nothing else up here adequately reduces power, right? So there's that. The second thing is that now this is our main thing, reducing the powers. Fantastic. This is just the z to the minus 2. So now we just need to grab the z to the 1 term in this expression. Okay? By grabbing the z to the 1 term in this expression, we can then determine the z to the minus 1 coefficient. Okay? It's a little convoluted, but the way they go about it, just bare basics, is saying, okay, if I is at least 1, then my lowest power I am dealing with is 2, which is this z to the z minus k pi to the power of 2. Okay, so it can't even be 1. It has to be 0. So this entire thing gets scrapped, turns into a 1. We're just left with this, and so just to get z minus 1 term, we go ahead, we grab one of these with the constant term in this square, which will just be this squared, which you can see right here. So that's the constant term squared times the z to the minus 1. So this together with that makes z to the minus 1. So that's this right here. Fantastic. And then we need to grab the constant term here, and then kind of the middle term, which will be 2 times this guy, okay? Which will give us this term over here. All good? All right, lovely stuff. We just refactor and we're happy, because that will give us all of our residues from that point forwards, okay? Because it is the c minus 1 term. All right, let's do this. So, Cauchy residue theorem, it's just now determining integrals using those residues, okay? So now we have the proper motivation for this method. We determine the integral about some closed contour, some simple closed contour, sorry, with the anti-clockwise orientation in omega, and we let these k points be all of our singularities, okay? Yeah. All right. And so integral equals 2 pi I times the sum of these residues. Lovely stuff. So let's immediately apply it. So first things first, classify singularities. Well, I see a 0 of degree 1 at 0, but there's no zeros on the denominator, so no removable singularities. We're just going to be looking at poles, okay? Factor it with respect to z squared first, and then factor that further. Mind you, we are... Oh, it doesn't say it here. My bad. We want to... Oh, never mind. Yep, all of them are simple poles, okay? Looking at B, we're just going to consider the ones inside the unit circle, so that'll just be the plus minus 1 on root 2 that we observed, and then we'll calculate the residues. So residue of the first one, simple poles, we just go ahead, multiply by the pole, and then limit it. We get 1 on 6 both times, fantastic, and then where is this going? Integral about a circle. Now this is a little odd, but usually we'll do this as a kind of parametrization. We're going to go backwards from that and turn it back into z, okay? About a circle. And so we define z equals e to the I theta such that our cos, just a moment. We want to, my bad, I was thinking of a different question. We're going to use our equation as before, turn it into a parametrization about a circle, the unit circle, and then recognize that formally this becomes I times the integral we're dealing with. and we're going to prove that, okay, we just calculated the residue. Fantastic. Its imaginary component, which is just the 2 pi on 3, is equal to the integral. Okay? So a lot of our integration now really just relies on algebraic interpretation rather than brute force, what is the area under the graph. So here is another example. And this is the time we're going to work it backwards. Okay? In this instance, we have cos of 2 theta. We want to show that cos of 2 theta over 5 plus 4 cos theta integrated between minus pi and pi is going to be equal to pi on 6. Okay? And the way we do this is we make a little assumption. Okay? We're going to say, okay, what does it look like when I re-represent everything in terms of z? Okay? Z being e to the I theta. Okay? We do this and we recognize this function, which can be decomposed into poles, all of which are unique and don't touch the zeros of the numerator. Fantastic. And because it is a unit circle that we are really traversing, we only need to consider the first two. Since minus 2 is outside of that, it is outside of our domain that we consider for the Cauchy residue theorem. So to calculate this, we go ahead, we say, okay, plug in minus a half, we work it through, we get minus 17 on 12. Once again, it was a simple pole, that's that. Next up, we go ahead, plug in z squared. Since this is degree 2, we need to take a derivative. Yeah. And so we get minus 5 and 4. We add them together, multiply by 2 pi I, and we get pi on 6, as required. Fantastic. All right, that is that for series. And we've finished that just on the dot of the hour. Next up will be Fourier and Laplace transforms. Now, this stuff, I think, is being covered at the moment, but it's fine. We're gonna be a bit ahead. This is also for revision for later on, when people are happy with it. But let's dive straight into it. Fourier transform. Some of you guys might have seen Fourier series in the past. If you've done your several variable calculus in term 1. But anyways, Fourier transform is pretty much just frequency domain. In some courses, that's how they refer to it. But right now, it is just a transformation of numbers, which is going to prove to be very useful and handy going forwards. So, first things first, given a function in L1, mind you, L1 just means continuously differentiable of the real numbers. So that is, it's like a certain definition on functions. Yep, converges then is finite. So that is the area under whatever graph is finite. Okay, it doesn't diverge. Anyways, Fourier transform of f, given by f hat, being a real number to complex numbers, is defined as f hat of, I'm going to call this one, what should I call this one? What should I call it? What should I call this letter? Huh? Okay, I'll call this letter Gary, okay? Fantastic. Okay, so f hat of Gary is going to be the integral from minus infinity to infinity of f of x times e to the minus ix Gary dx, okay? And it's not the most intuitive just yet, but if you looked back at how several variable calculus did it, they defined this kind of notion as breaking it down into different norms of functions, where they would do Fourier series. Mind you, Fourier transform is just the continuous analog of Fourier series. It's basically where your period goes down to, your period goes to infinity. But anyways.
I looked it up. It's a frequency variable.
Yeah, it is.
Yeah, that's just the name for it.
Yeah. We love electrical engineering. Anyways, Fourier transform. Now, mind you, while we have the Fourier transform, we have the inverse Fourier transform, which is just saying that if you have a function that is integrable called MR, you can define the inverse Fourier transform just by doing the exact same thing with respect to Gary and dividing by 2 pi. Okay? That's all. Yeah. Yeah. All right. Let's jump into an example. Let's not give the answer away too quickly, but we want to find the Fourier transform of the function f of x equals e to the minus absolute value of 4x. Okay? So let's go ahead. We have the Fourier transform of fx equals f hat Gary equals integral minus infinity to infinity of f of x, which is going to be e to the minus absolute value for x, and then multiplied by e to the minus I x Gary dx. All right. Now we have an absolute value here. We want to break it in two. So we take the positive and the negative versions, okay? Because this is a real integral, so we don't need to worry too much about it. So integral 0 to infinity of e to the minus 4x, e to the minus ix Gary, and then likewise plus the integral from minus infinity to 0 of e to the 4x, e to the minus ix Gary dx. Okay? And so this is just really grouping them together and then factoring Gary and his friends out to the front. We perform our integral as per usual. One important thing to note here is just going to be, since it's with respect to x, and x is now attached to a real component, as x goes to minus infinity, or as minus x goes to still minus infinity, those bits go to 0. So we only really take these components, which should give us this fraction minus this fraction, okay? Which gives us as desired. Calculates f hat of Gary. Fantastic. So that was a quick intro to a Fourier transform. We don't really touch it too much in this course, but then it comes into Laplace transforms. Now, before we just dive straight into Laplace transforms, let's define a new kind of notation, a new data, okay? Exponential of type A. What does this mean? It simply means that the absolute value of a function can be related to the scalar multiple of an exponential function with a coefficient of A, okay? So the exponential coefficient is A, the actual coefficient is C, okay? C is just some real number that is sufficiently large, has to be finite. You can't say, oh, C goes to infinity, therefore it is every exponential type. No. All right. Yeah, so it's just saying absolute value of that function is less than or equal to this manner of expression. All right. We note that there's also exponential of type A+, which is just for all A that is whatever A value specified and greater. Okay, so I could say exponential of type 3. So that's just saying ft is less than or equal to c e to the 3t. Okay, that's that. So one such function that is not going to be exponential of type anything would be e to the t squared. Okay, just because as t goes to infinity, it's going to need a bigger a value, and that is not how finite values work. So we proceed. All right, so the actual Laplace transform, it looks very similar, except we use z instead of Gary. Gary. Yeah. Now, we're only really able to do this given that z is greater than a, okay? Where a is our exponential of type a, that is relating to f. Okay, so if f is of exponential type a, then over h of a, which is the half plane that is greater than a. So if let's just graphically describe this. If I get a as 3, we love 3. Over this region to the right, what we observe is that this function holds for the Laplace transform. Okay? And it has a lot of properties, which is the reason why we use it. We don't really care too much about what it actually does as of right now, but let's see what it does. Okay, here is an example. We're going to find the smallest number a such that sine is exponential of type a. Okay? Now, there's a couple ways to think of this. If sine is exponential type a, then there is a certain bound at which it has to follow very close to the start, especially since we're considering just sine on real numbers. Okay? And so, we go ahead and think about it. Sine is not bounded above 1. Sorry, sine is bounded by 1. And so we just think that not necessarily all s will work, and more particularly, any s less than or equal to 0 will not work because that's decaying. Okay? So we have to think going towards 0. Okay? And well, I mean, exponential functions technically 0 works, where it's just a constant function at 1. So that's that. So we've determined the type, and now we can perform the Laplace transform on sine of t. So we recognize that z is an element of the real component. No. Z is such that the real component of z is greater than 0. Okay? So this is just saying that it is on the right half plane. Fantastic. Now we can go ahead and perform the transform, which is just going to be integration by parts, right? Yeah, not too much to elaborate on that. You perform by parts twice, so that you can use the funky little integral formula trick and put the result in terms of my initial and then just refactor it. To get that, the Laplace transform of sine is just given by 1 over z squared plus 1, given by the right half plane. Fantastic. All right. So, I don't even know what I'm up to. I'm not going to say first things first. Might be a fourth, as they usually go. So, Laplace transform, properties of the Laplace transform. Here they are. So, differentiation works in a very funky way in the Laplace transform, okay? So, it's a little funky, but our best friend is coming up soon, okay? And unfortunately, it's not Gary. Also, we can consider, I think you would call this frequency shifting, but anyways, this is how you shift functions across left and right. So if my function is multiplied by e to the minus at, it is just pushing the Laplace transform of that function with it in that direction. Okay, so by saying minus at up here, that translates to push it to the left by a, right? Okay. Mind you, this is with appropriate changes in the domain. Anyways, now we hit the big one. This is our best friend. For anyone who's done differential equations, this one is, it can be a lifesaver. But anyways, we get little things from just substitutions in integrals, which give us this result, number 3. But number 4 really takes the cake. It says that if we take the Laplace transform of a derivative of a function, it equals something rather unique on the S domain, okay? A multiple of your original function minus its initial conditions. Now I mentioned differential equations, and you'll see that in just a jiffy. So here's a little example. We're going to show that the Laplace transform of the nth derivative of a function is equal to z to the n of the Laplace transform plus minus yada yada, all being initial conditions, okay? So we can consider this in a few ways. First of all, induction does work, I suppose, where you say, okay, if I take f dash and I Laplace transform that, then what I get should be z Laplace of f minus f0. Okay, but then if I sneakily add a dash on everyone, then what that turns into is Laplace of f double dash goes into z of Laplace of f dat. Hey, I need to work this out. So I'll just write it out in full for now. Z of, you just do it again. This will be Laplace of f minus zf0. Okay, actually, this will be z squared, zf0. Yep. Minus f dash 0. Okay? So that's the kind of thing we're talking about, where we just keep on taking it and taking it. We get z to the n there. We keep just one of them over here. Everything here onwards remains the same, just gets hit by another derivative, and so forth. So inductively does work, but there's not too much to talk about here. Anyways, as mentioned before, as mathematicians, we love inverses for some reason. We like undoing all of our messes, surprisingly. And so if f is from 0 to infinity to c, and is of exponential type a, then we can regain our original function from the Laplace transform, okay, given by this formula. There's not too much to talk about in terms of this. But yeah, you can talk about the residues form of the inverse Laplace transform, as it is over here, which acts as a few things. It acts as an upper bound, as well as a certain holomorphic function. But yeah, these are just certain methods we can use to recover the function. Okay. Convolutions, pretty funky. Just define a convolution by this method. Wait a minute, is this even in the course anymore? I'm actually wondering, because
This wasn't in log.
Yeah. This actually might not be in the course anymore, but we'll just go ahead. Yeah, because I finished the slides, and it's not. I think what they did was they removed a bunch of slides because they thought it wasn't super relevant to complex analysis. But like, I mean, yeah, it's not the most relevant to complex analysis, but it's cool. Anyways, we're nearly done. We'll just go through it anyways. Basically, we recognize convolution as something we typically used in probability, if you took that last term. Basically, it goes ahead and it says, if I have two lists, they're labeled 1 to n, 1 to n, then you take them from alternating sides and you just add them together. That's the easiest way to explain it, okay? And that becomes your integral. Anyways, Laplace transform has the property such that a convolution on the time domain being, f and g on their own, translates to a multiplication on the Laplace domain, okay? Fantastic stuff. Few more things on differential equations. We got f of t given this. They sneakily call this the Volterra integral equation, and we can actually use the Laplace transform to deal with it in a pretty interesting way. So, some things to note is that this function can be recognized as the integral of this one. And so, if we just look forwards a little bit, we'll recognize that when we try to solve this, we just take the Laplace transform of everything, and given it is linear, it separates out. The convolution turns into a product, and we're able to break it down. We refactor to get our original Laplace transform value. Yeah. You could use residues. But it's a little bit irrelevant to this course. Let's just read through it a little bit. I guess since there's so much free time, before I say goodbye, does anyone have any questions they would like to ask me? Anything. Could be not ascertaining to this. Alright, fair enough. Okay. Well, that brings the complex analysis revision seminar to a close. Thank you for coming. Thank you for watching online. Good luck with your studies. And I hope you guys do your best. All right. Enjoy.